So let's look at the read key handler. Now this is what we're going to do for the supervisor call. And so the intent is that we're going to go off and we're going to go find out which kernel buffer we should be accessing, which of the virtual kernel buffers for the, all the different virtual keyboards. So there's a keyboard that's associated with our particular process. And we're going to go off, and we're not going to talk about the details of how to read from that circular buffer, although we'll talk about that in a couple weeks. But for now, we'll just assume there's a read input buffer that you give it the keyboard number. It says, oh, I'm going to go get that. Remember that A we put in the previous slide? We're going to fetch that out and advance the pointers appropriately. And we're going to put that into this user data structure in the location that the user's R0 was stored into. So we're getting rid of whatever the user had in R0. We're going to put in the keyboard character now. And when we return here, when we fall off the end of the handler and go back to the assembly language we looked at last time, what happens is that we busily restore all the registers, including the modified R0, back into the hardware registers and then resume execution of the user's program. So that's all good. So when we had a character, that was good. However, if there is no character, okay, well, option one, we want to wait. So suppose we just sit here and loop in the kernel, saying, while the keyboard buffer is empty, nothing to do, I'm just going to sit here and loop. Well, there's a problem with this. And it says on the slide, but hopefully you all can, well, it says on your handout, we'll say on the slide in a second. Okay, and the problem is that if you do loops in the kernel interrupts are disabled. So if you're expecting the interrupt routines, the interrupt handlers to be filling the keyboard buffer, they're the ones that would actually make the buffer be not empty. They never get executed because the IRQ is being ignored while we're in kernel mode. Right, so this notion of looping in the kernel is always a very bad idea. If you're ever tempted to write a loop in the kernel, don't, because that'll be the last thing you'll ever hear from your machine. You'll get to repower it up again and say, I better go fix that. And goodness help you if you've put it in a place that when it powers up it happens, because now you have to go start from scratch again. Get rid of that disk and put in a new disk that doesn't have the operating system code with that bug in it. So I've done a little bit of that. There's nothing more frustrating than turning on a machine and having it sit there autistically, and you're sort of going, oh, dang. Okay. Have to figure out what went wrong. Steve and I used to sit down the street in the garage. The garage is no longer there. Working on a little IBM time traveling system for a brand new little IBM computer that had just come out. And I tell you, it was really frustrating to sit there and the lights freeze and you go, what to do? Okay, so this doesn't work. So how should we fix this? So we're going to rewrite our loop, and we're going to rewrite it the following way. We're going to do this notion of writing loop. We want to loop, but we don't want to loop in kernel mode. So instead what we'll do is we'll back up the saved PC, or the PC plus 4, which was normally pointing to the instruction after the read key. We'll subtract 4 from it. Now the XP register, which has the PC that has the value that we put on the PC when we return to user mode, we've backed it up. So it's, now what is it pointing to? It used to be pointing to the instruction after read key. Now it's pointing to the read key instruction. So when we return, what will happen? What will be the next user mode instruction that gets executed? The read key. And you're sort of going, whoa, that seems like a lot of work, Chris. I mean, what's the point of doing that? So what is the point of returning to user mode to execute the one instruction which we knew just failed anyway because we didn't have a character? Why all this trouble of returning to user mode for one instruction? Right, because once we're in user mode, if there's a keyboard interrupt waiting, the IRQ, instead of executing that instruction, will say, aha, I have something else to do. Sorry, read key. I'll get back to you in a moment. So this notion of returning to user mode is sort of key to making a loop. So our notion of a loop currently consists of, okay, I can't loop in the kernel, but if I return to user mode, then interrupts are enabled, and eventually this will a keyboard interrupt will happen. We'll have a character, and we return it to the user. Yes, ma'am?
Don't you only have like the time it takes to implement one instruction, which is extremely fast?
It's extremely fast, but remember what we're doing is that somewhere along the line in this complicated loop, okay, in which we have a lot of instructions in kernel mode and one instruction in user mode, somewhere in that list of instructions, the interrupt request will be asserted. And at the exact moment that we return to user mode, now your beta hardware, which is looking at IRQ at every instruction and checking the higher order bit of the PC, will say, aha, now I can service this interrupt that somehow. So it's not like the interrupt has to happen magically at that one instruction. It will just be serviced when the user mode, the PC 31 is 0 again for being in user mode. So this one actually works. It sort of wastes a lot of time because we're continually going back and doing read key, read key, read key, and you're sort of saying, wait a minute, this is silly. I don't have any character to give you, right? And maybe we could tell you to shut up for a while, and I'll get back to you when I have a character. If you were the kernel, you'd sort of, you get a little impatient with this user mode program. And if you were another process running on the same machine, you might be saying, look, give up already. We don't have a character for you. Can't we go run some other processes more productively? And the answer is, yeah, that's actually a very good idea. So in addition to simply backing up the program counter for the program that had the read key in it and looping there, we'll back it up so the next time we run that program, we will indeed execute the read key again. But instead of just going right back and doing that, what we'll do instead is to move on and try give every other process a chance to run. Right, so if there's other runnable processes, they don't lose out. Right, they get their turn as normally. And then eventually we'll get back to the process that wanted to do the read key, and it will try again. And if in that few tens of milliseconds it took for us to get back to that program, their keyboard interrupt happened, great. It gets this key. Otherwise, we just keep doing that process where we keep checking in with the program saying, well, we stopped you, try your thing again and we'll see if it works, and if it doesn't, we'll try everybody else for a while. So it's sort of a round robin thing where we keep trying the user here. Right? Everybody sort of okay with that? I mean, you sort of see how we're solving this busy wait. We went back to user mode, which is good, and now we're no longer sort of continually wasting our time doing read keys to no effect. Okay, so this is better. This is better. Everybody else doesn't really notice that there's one program waiting for the keyboard interrupt. But there's still some inefficiency here. There's still this notion that I'm getting back to you. The kernel gets around to rescheduling, the program that's doing the read key. And it's a little funny because the kernel certainly would be able to tell whether there was a character. So if we knew what the program was waiting for, we wouldn't bother, the process was waiting for, we wouldn't bother rerunning it until whatever it was waiting for had actually happened. And the kernel would know when that happened because we could make the keyboard handler say, aha, if there's anybody waiting for a key, there's one now, so maybe you should try running them again. So our final step here is to notice that even though this works, what I'd like to do is to get the ultimate efficiency and simply not waste any time running processes that I can sort of tell will not succeed. So this slide has a lot of text in it. It's a little easier to see what happens sort of graphically on the next slide. So this is here to look at, but let me sort of describe what happens. Let's first of all look at the changes I made here. I don't call scheduler. I call a routine called sleep. And I give it a magic number. In this case, it's just so long all the magic numbers that for reasons you go to sleep are unique, it doesn't really matter how we choose the numbers. In this case, I've actually chosen the address of the keyboard buffer or something like that, which is unique. And so long that the sleeper and the people who do the wake-ups agree on these magic numbers. Okay? But just think of this as before you fall asleep, you've pinned a note on your blanket saying, wake me up in time for class tomorrow, 9 o'clock. And so now your roommates or the kernel scheduler knows what you're waiting for and doesn't keep waking you up and say, was I supposed to wake you up now? Oh, sorry, go back to sleep. That would be pretty annoying. And so what we're going to do here is we're going to sleep where we've indicated this special reason why we're sleeping. We're waiting for a key to appear on a particular virtual keyboard. Now the sleep routine, simply we create a new entry in our process table, which is the process's status, which indicates what you're waiting for. So this magic number sits there. And the scheduler, okay, and then we call the scheduler, and the scheduler simply skips all the processes that have a non-zero status. So if your status is non-zero, your status word is non-zero, we assume you're waiting for something. And so we don't bother running it. So we're only running processes that are runnable. And in fact, if you do a PS dash AUX or something on your Linux system or your Apple system, or you look at the task manager under a Windows system, you can look, there's a status field for each of the processes that says whether it's waiting or it's runnable, if it's sleeping, what it's sleeping on. And so this is exactly what happens in most operating systems. You can read the note that's pinned to the blanket as they sleep. Okay, so that's fine. We've understood how people go to, yes?
In this case, if all the processes have a status that's not 0, what's going to be true? Because if they don't have the means of keeping the status while you're there.
Yeah, so you would certainly want not to build one of these kernel loops by the sort of accidentally not having any running processes. So probably there's a null process the kernel goes and executes, if it doesn't have anybody else. And so that would be a clever little bug where everything would be great except, every third Tuesday, the kernel would suddenly freeze and you'd say, it was working so well. And so that's a very subtle bug, and one that presumably the Linux people have figured out how not to build a really complicated kernel mode loop, which would be just as disastrous as a stupid one. Although much more interesting, yes. Okay, so now what does the keyboard handler do? Well, it does the same thing it did before. It goes off and fills up the buffer, but now it's going to start the wake-up process, but not for everybody, only for those processes that were waiting for that particular keyboard buffer to be filled. So it's going to do a wake-up, and the wake-up routine searches through the process table, looking for anybody that was waiting on that particular magic number, that keyboard num, and it sets their status to 0. So now we're pointing out and says, okay, over here, you can run again. There's a keyboard in there, a key character in the keyboard buffer. The read key will succeed, at least for one of you. So we'll wake you up if multiple processes are waiting on the same keyboard. We'll wake them all up, and the first one to get run will succeed, and everybody else will say, oh, dang, it's empty again, and go back through the whole process. Everybody sort of get that? That's sort of a fairly complicated way so that we can deal with processes that have needs in a way that doesn't impact the running of other processes that might stall waiting for something, and we'll go from there.